Today we're going to look at solving systems of linear inequalities when our boundary lines are parallel. So let's get started. When we're solving systems of two linear equations or inequalities, when we have different slopes for our lines, we will end up with a solution when we're working on a two-dimensional plane, like we have here. So with two equations, any two lines that have a different slope, so here we have a slope of 1, and with the second equation we have a slope of -2, these two lines are going to cross someplace. They're going to intersect. And where they intersect, that's the solution. That's the one point they have in common. It's that ordered pair, that x-coordinate and y-coordinate. When you plug those into both of the equations, you're going to end up with a true statement for both. So with two linear equations, you're going to end up with one point that is a solution to the system. When we're looking at two linear inequalities, to find the solution, the first thing we're going to do is graph each of those boundary lines. When we graph these two boundary lines, this divides our graph into 4 different regions. And then we need to determine which region to shade for each of these inequalities. That one region where everything overlaps, that is the solution to this system of inequalities. And in this case, for this specific example, where these two boundary lines intersect, that's not a part of the solution because that point is not on the first inequality, which was y greater than. And so they do not have that point in common. So when you're looking at systems of two linear equations or inequalities, if the equations or the boundary lines of these inequalities have different slopes, you will have a solution. For linear equations, it'll be 1 point. And for linear inequalities, it's going to be a region on the graph. And there are an infinite number of points in this region. Now let's look at special cases when we're talking about two linear equations. So here we're only looking at equations. And with special cases, they're going to have the same slope. You're going to have one of two situations. If you have the same slope, so in this case, we have a slope of -1, but a different y-intercept. You have different lines. And these two lines, again, in our two-dimensional xy coordinate plane, these two lines are never going to cross each other. They have the same slope. They're changing at the same rate. These are parallel lines, and we end up with no solution. They never cross. They have no points in common. The second situation is when you have two equations, and although these two equations, they look different, they actually represent the same line. This second equation that's written in standard form, if we write this in slope-intercept, we end up with -x plus 3. That's the same equation. So we have the same slope and the same y-intercept. So these two equations, they represent the same line. And in this case, we're going to have infinitely many solutions because every point that's on these lines, and there's an infinite number of points on these lines, they're all solutions to this system. Again, when we're looking at two linear equations, we have special cases when the two lines have the same slope. They're either parallel lines, meaning they never cross each other, so there's no solution, or they're the same line. And in that case, we have infinitely many solutions. Now let's look at two linear inequalities. And today we're going to look at what can happen when our two boundary lines are parallel. And in a later lesson, we'll look at when our boundary lines represent the same line and see what we can get there. So for this system, we have y greater than or equal to -x plus 3 and y less than -x plus 1. So our boundary lines, y equal to negative x plus 3 and y equal to negative x plus 1, they have the same slope. They have a slope of negative 1, a different y-intercept. We have parallel lines. We look at this first inequality, y greater than or equal to negative x plus 3. We'll end up shading the region up and to the right of this boundary line. And for y less than negative x plus 1, we end up shading the region down and to the left. There's no overlapping region here. We have parallel lines with no solution. Now let's look at very similar inequalities. All I've done is flip the direction of the inequality signs. So we've gone from 1 greater than or equal to negative x plus 3 to y less than or equal to negative x plus 3. And for the second inequality, we have y less than negative x plus 1. And here we have y greater than negative x plus 1. Same boundary lines. And then looking at that first inequality, we're going to end up shading down and to the left for y less than or equal to negative x plus 3. And for the second inequality, y greater than negative x plus 1, we shade up and to the right. Now we have an overlapping region. And that is our solution to this system. This is the graph of this system of linear inequalities. So in this case, we have parallel lines, and there is a solution. So it's not as cut and dry as we saw with linear equations. So let's practice solving a system where the boundary lines for the inequalities are parallel. So here we have two linear inequalities, y greater than x plus 3 and y greater than or equal to x plus 2. So we'll start by plotting these boundary lines. So we have y greater than x plus 3. The boundary line is y equal to x plus 3. So we have a y-intercept of 3 and a slope of 1. So to help us graph this, a slope of 1, we could rewrite this as a fraction. The fraction would be 1 over 1. So that means we're going to go up 1 and to the right 1. So starting at that y-intercept of 3, we're going to go up 1 to the right 1. Let's do it one more time, up 1 to the right 1. And then with these 3 points, we can graph our boundary line. Now let's test a point on either side to see what side we need to shade. So let's test 0, 0. And then this is 0 greater than 0 plus 3. So 0 greater than 3, that's not true. Let's try negative 3, 3 as well. So we have negative 3, 3. So we have a y value of 3 greater than negative 3 plus 3. 3 greater than 0, that is true. So we'll shade up and to the left of this boundary line. Now let's look at this second inequality. We have y greater than or equal to x plus 2. So our boundary line is y equal to x plus 2. We have a y-intercept of 2. And again, we have a slope of 1. So we can rewrite this as 1 over 1, meaning we're going to go up 1 and to the right 1. So starting at our y-intercept of 2, we go up 1 to the right 1. Now a unit of 1 is somewhat small. We could rewrite this slope in a different way if we wanted to. Again, we have a slope equal to 1. Well, negative 3 over negative 3, that's also 1. Negative 3 divided by negative 3 is 1. So instead of going up 1 to the right 1, we could also go down 3 and to the left 3. So from our y-intercept, we go down 3 and to the left 3. And then with these 3 points, we can draw our line. Again, the second inequality has a solid line. because the points on the line are included in the solution, since we have greater than or equal to. With the first inequality, this is a dashed line because the points on the line are not included in the solution, since this is only y greater than. The equal to is not a possibility. So the boundary line itself is not included. So with this second inequality, let's test some points. We'll start with that 0, 0 first. So at 0, 0, we have 0 greater than or equal to 0 plus 2. This is 0 greater than or equal to 2. That's not true. And then let's again pick negative 3, 3. So this is 3 greater than or equal to negative 3 plus 2. 3 greater than or equal to negative 1. And that's a true statement. So we're going to shade up and to the left for this inequality as well. So what do they have in common? What they have in common is this region that's up and to the left of this red boundary line. So we'll shade that region. So although in this system we do have two linear inequalities, the solution to this system is simply the inequality y greater than x plus 3, shown by this red dashed boundary line, and the purple region shaded up and to the left of the boundary line. A great way to learn is to practice on your own. We will discuss in a bit, but go ahead and pause your screen and do these two problems. So we're asked to solve the following system of linear inequalities. We have two linear inequalities, and let's solve this by graphing each of these linear inequalities separately. So with this first linear inequality, we're going to write and graph that boundary line. In this case, the boundary line is dashed. Now we need to determine which side to shade. Again, I like to select that origin, 0, 0, and test that point. We end up with a true statement when we test the origin. But let's go ahead and test a point on the opposite side as well. We'll do negative 3, 4. Again, that does lead to a false statement, as expected. So we're going to shade down and to the right of this first boundary line. Now let's repeat this process for the second inequality. It's currently written in standard form. I went ahead and converted the boundary line to slope-intercept. And then from here we can see our two boundary lines have the same slope, 2/3, but a different y-intercept. So without even graphing the second boundary line, we can see that the lines will be parallel. But again, graphing this boundary line. Now let's determine which side of the boundary line we're going to shade. We'll start with that origin, 0, 0. This does not result in a true statement. So let's try a point on the opposite side of the boundary line. We'll go with 0, 3. 0, 3 does lead to a true statement, so we're going to shade up and to the left of this boundary line. The solution to this system will be the region where these two inequalities overlap. So that's the region between these two boundary lines. And then this region is the solution to this system of linear inequalities. It is the graph of this system. And looking at this second problem, we have the system containing the linear inequalities y greater than or equal to 3x plus 4 and y less than 3x. By looking at these two inequalities, we can see our boundary lines will have the same slope, a slope of 3, and they have a different y-intercept. One intercepts the y-axis at 4, and the other one at 0. So again, our boundary lines will be parallel. Let's look at the first inequality. So our boundary line is y equal to 3x plus 4. We're going to graph that boundary line. It's a solid line. Let's try that origin again, 0, 0. That does not lead to a true statement. Testing the other side, we have negative 3, 0. And that results in a true statement. So we're going to shade up and to the left of the boundary line. And then looking at that second inequality, our boundary line is y equal to 3x. The line is dashed to show that the points on the line are not included in the solution. Again, I still like to pick that origin, but since this line, this boundary line goes through the origin, I cannot pick that point. So let's go ahead and just move to one side or the other. We'll test the point 2, 0. That does result in a true statement. But let's confirm by testing a point on the opposite side of the boundary line. And negative 3, 0 will work for that. So testing negative 3, 0, that results in a false statement. So we're going to shade down and to the right of the second boundary line. These two inequalities have no region that overlaps. So this system has no solution. Drop any questions you have in the comments. Continue practicing solving systems of linear inequalities, and I'll see you in the next video.